our first speaker of the afternoon is Justin Khoury.
Is the music going to keep going during my talk? Or? It's kind of nice, and maybe. Yeah, might put people to sleep. Okay, very nice. Thank you very much to Matt and Kendrick for inviting me to this very nice workshop. So I'm going to talk about some work that I've been doing for the last year or two together with Lasha Berigiani, and I'm going to mention some ongoing work as well with these people, including Tom Lubensky, who is a condensed matter theorist at Penn. No, but seriously, is it possible to turn off the music? Okay, thank you. All right, let's get started. Very nice. So I don't have to convince people here, but I think if we ask ourselves what is the most convincing piece of evidence for the existence of dark matter, let's say the most unambiguous one, it comes from the largest scales. If you press a cosmologist, that's what most cosmologists would tell you. This beautiful map of the power spectrum from the Planck satellite, I think reproducing these features in the angular power spectrum without dark matter would be extremely highly challenging, as well as the success at reproducing the power spectrum. But if we think about it, on those scales, we're really only using the hydrodynamical approximation for the dark matter. It's a very good approximation to just assume that the dark matter is described by a perfect fluid, described by some energy density and some pressure. And as long as the perfect fluid has small enough pressure and equation of state, then in principle, any such fluid can do a very good job at reproducing this data. So the key message, of course, is that there is a lot of room, in principle, for new physics occurring on galactic scales. So let me mention a few facts about galaxies, empirical facts about galaxies. Okay? Because if I start by telling you MOND, some people blood pressure goes way up if I say MOND. Okay? So these are facts. It's empirical statements. Okay? This is not anything about theory or. Okay, so there are some, I think, pretty remarkable facts, regularity displayed by galaxies. The first one, of course, is the Tully-Fisher relation, which was extended by Stacy McGaugh to be the baryonic Tully-Fisher relation, which basically is the statement that the total baryonic mass, including gas plus stars, is proportional to the asymptotic velocity, the flat velocity in the rotation curve, to the fourth power. Now, this relationship is shown here with data. Okay, the black line is this v to the fourth fit. Okay, the dashed line is the prediction of Lambda-CDM, assuming a constant fraction of baryons independent of mass, etc. Okay, just taking the mean. Okay, so of course now naively, if you include feedback, you expect that as you go to smaller velocity, smaller mass, halos are more susceptible to losing their baryons. You would expect a steepening of this relationship. But what is striking, and maybe fourth power can occur, but what is surprising is the tiny amount of scatter that is observed. Okay? If feedback processes are responsible for this relationship, ultimately you would expect much larger scatter. In fact, when you do the analysis, the scatter that's observed about this v to the fourth at the moment is consistent with 0 when you take into account observational errors. Okay? So another observational interesting fact is known as the Freeman limit. Okay? So Freeman limit is the following statement. As is well known, one of the indirect evidence for the existence of dark matter in galaxies is the following, that if you have a disk galaxy, if you have just baryon in a disk without any dark matter, then this disk tends to be unstable, the formation of bars, other instabilities of this sort. Okay? So the fact that, in fact, the disk is stabilized is due to an isotropic halo of dark matter surrounding it. That's how you would interpret it. Now, in principle, of course, in a fixed halo, a halo of fixed mass, if I have a disk and I make the disk bigger and bigger, at some point the disk will go unstable in some sense. But in CDM, in principle, for a given disk, I can just build a large enough halo. Imagine that it's surrounded by a large enough halo to stabilize it. Okay? So in principle, you shouldn't see any upper bound, in principle, to the brightness of disk galaxies. Whereas, in fact, observationally, there seems to be a cutoff. It's not a firm cutoff, but it seems at some point it kind of level. You don't see galaxies above a certain surface brightness. Now, I should have said, of course, if you ask about both the normalization of the Tully-Fisher relation as well as this cutoff for the surface brightness, they both involve an acceleration scale, which numerically as an empirical fact ends up being this A naught, this famous value of A naught, which is about 10 to the minus 8 centimeter per second squared. Okay? Similarly, for surface brightness, it's also acceleration scale. You're talking about the Freeman law now? I didn't understand your point. Can you say again? No, I'm saying in principle, there's no reason why you cannot have 10 times more bright disk galaxies. That's all I'm saying. Why it should level off at that point. That's all I'm saying. Yeah. Huh? No, but in principle, you could have them. CDM could, in principle, accommodate large enough halos that you could have disk galaxies that are 10 times brighter, in principle. OK, this is a very interesting, another interesting fact. People, again, purely empirical fact. If you look at the surface brightness, of course, in quotation mark for the dark matter, in the center of galaxies, meaning, so people have, this is pretty model independent. You assume, you basically have, you fit to a chord isothermal profile, more precisely a Birkett profile. And basically this, what you infer here is the central density, the density in the core, times the size of the core. Okay, this is a measure of surface, if you want, the surface brightness, but now for the dark matter itself. And what people find is basically that this quantity ends up being essentially constant. Okay, there's very little variation of this amount of surface. So this is the surface density, if you want, of the dark matter in the central regions of galaxy, even though independently the central density and the radius of these cores varies tremendously as a function of the luminosity of these galaxies, the product is essentially constant. And it's constant. This ranges from the dwarf spheroidals at the low mass end to ellipticals. Okay, so this is it's pretty striking. Why this conspiracy? And again, if you ask, if you plug in, this is again an acceleration scale, and if you plug in again this A naught, you get bang on roughly the central value of this. So again, these are just empirical statements. So I just want to say, of course, these kinds of relationships are embodied in the MOND empirical law. I want to stress, not a theory, okay, so that people's blood pressure doesn't shoot up. It's not a theory, it's an empirical fact. Namely, even if you believe that it's just genuine WIMPs, you like WIMPs, perfect, it means this law must come out. It has to come out from the complicated physics of baryons inside galaxy feedback processes. It has to come out because it's true. So this simple statement that Milgram came up with, that the acceleration law somehow effectively becomes the square root geometric mean of Newtonian acceleration due to the baryons only and this characteristic A naught, does exquisitely well at fitting rotation curves. I've circled one, by the way. This is one of the low surface brightness galaxies. Keep an eye on this one because we're going to come back to it in a minute. Of course, as a consequence of this law, both the Tolley-Fisher relationship as well as Friedman's limit come out as predictions, or as statements, let's say as consequences, as well the surface brightness, the dark matter surface brightness, at least in high surface brightness galaxies, is precisely given by this ratio. So this is just to say that this is an economical way to encapsulate these empirical facts of galaxies. Again, it's not a statement about WIMPs or whatever. It has to come out. So those are the facts, okay? This scale, A naught, is in the data. It's there. So now you can have 3 attitudes. Well, you can have 4 attitudes. The fourth one is you ignore it. Okay, so we're not going to take that attitude. So you cannot completely ignore it because it's there. So you can have one of 3 attitudes. One, which I think is the majority of the community, is that it's all due to feedback at the end of the day. Namely, the dark matter particle may be very simple, like a WIMP, with no particular interactions with baryons, and that, in fact, once you include all the complicated processes of actual galaxies, you put it all in the mix, and out comes this MOND effective law, okay, as an outcome. Now, the question is, first of all, these simulations are very complicated. They involve many processes that are parameterized. They're not computed by first principles, of course. But even if you believe, and by the way, of course, in simulations, one is actually tuning these parameters to get, on average, Tolley-Fisher relation. It's not a prediction, once again. But even if you believe that you're going to tune your simulations to get v to the 4th on average, as we said, what is surprising is that these processes, which are all stochastic, how can it be that they give rise to such tight correlation, such little scatter? Seems to me very unlikely. And indeed, at least in some simulations, this is from Illustris, you should, the dots and the squares are simulated galaxies, and you should compare these galaxies to the yellow band, which is the Tully-Fisher relation, okay? I can explain these other guys, but you should focus on the yellow band. And you see, by the way, these guys were 1 by 1 tuned to get v to the 4th, but you see that the scatter is much larger than what's observed. Now, in more detail, this is very interesting. So this is from the Eagles collaboration. You can look now at individual rotation curves, not just the Tully-Fisher relation, which is a normalization, but individual rotation curves, and ask how well do they do, the simulated ones compared to actual data. So let me explain this a little bit, because it's actually quite interesting. So these are the rotation curves. So here you see 4 particular galaxies. The black line is the dark matter only rotation curve. Whereas the colored band is the range of rotation curves you get by including feedback. Okay, so you get a range prediction. So the first thing to notice is that you see that you get some range. Of course, feedback does play a role. However, you see that the shape of the rotation curve isn't dramatically altered. You need a change in normalization, but the shape is not dramatically changed. Furthermore, these and the data, of course, for actual galaxies are these various data points with error bars. Now, what you can see is that for the 4 galaxies that I've shown here, this is the point of their papers, it's the unexpected diversity of these rotation curves for dwarf galaxies. So notice that the asymptotic velocity of these 4 objects is almost roughly the same. They're all of order 80 or so, or 90 kilometers per second. So they're all roughly. So first of all, the fact that they have the same asymptotic velocity tells you that by the baryonic Tully-Fisher relation, they have the same amount of baryons in them, first approximation. And also, since the asymptotic velocity is also a proxy for the dark matter, they also have roughly the same. They live in similar mass halos. Okay? So despite the fact that they live in similar halos with the same amount of baryons, nonetheless, you see that the rotation curves look dramatically different. This one here is similar to a high surface brightness, cuspy type profile, where you rise up sharply and then approach flat. Whereas this guy over here has this very slow, gradual linear growth in the rotation curve, suggestive of a core of dark matter. It's a core, by the way, which is of order 8 to 10 kiloparsec in size. It's a huge core, okay? So how can it be that galaxies that form in halos that look pretty much the same, with the same amount of baryons in them to first approximation, how is it that they arrange themselves in such different fashion? And by the way, this galaxy here, you'll recognize, is the galaxy that this MOND phenomenological law had no problem fitting. Okay? All right, so now, that was attitude number 1. I call it the conspiracy. There is no, in my mind, it's a conspiracy for just whims to match these striking properties. The other extreme, in my opinion, which is espoused by a small percent of the community, is to say, well, given this, and given that MOND works so well, maybe MOND is somehow fundamental. There is no dark matter, okay, and it's actually a fundamental change to gravity. Now, I don't espouse that view, but I'm going to show you nonetheless, because it's going to be important later in my talk, how actually you would go about getting this modification of gravity as a theory, as a Lagrangian. So the way it's done is as follows. This was noticed by Bekenstein and Milgram 30 years ago. The simplest way to get it is to couple a scalar field, a new scalar field which is going to mediate a force. You couple it to baryons. The simplest way is through a conformal coupling, trace coupling of this type. And you need this very funny kinetic structure, okay, d phi squared to the 3/2 power. And of course, as a field theory, this looks silly, okay, to have non-analytic powers of kinetic term. It looks completely ridiculous, okay? But nonetheless, let me show you why you need this particular non-analytic power. If you vary this action with respect to phi and assume static spherically symmetric source, whatever, you find precisely because it's 3/2 in the equation of motion, you get this nonlinear Poisson equation with precisely grad phi squared inside. And when you go ahead and solve this, you integrate it because you had grad phi squared. It turns into the square root of the integrated mass, and that's exactly the square root that you needed for at least the asymptotic MOND regime. You add this to gravity, and then the total acceleration is the Newtonian acceleration plus this scalar-mediated force. And this form of the total acceleration is exactly one of the examples of things that will give you the right asymptotic regimes. At high acceleration, you recover Newton. At low acceleration, you recover the square root. Okay, so that's one way to do it. But of course, I mean, this is equally as much a conspiracy. If it's all modified gravity, how in the world are you going to reproduce these beautiful fits that are so consistent with collisionless particle dark matter? Okay, so it seems this is it's a very big challenge to actually reproduce those observations. Also, if you take MOND literally, it also has problems fitting galaxy clusters. It's a well-known fact that galaxy clusters have approximately isothermal profile. The temperature in X-ray is approximately constant in radius, whereas MOND would predict a steeply rising temperature profile. So it seems to work really well in galaxy scales, but if you take it literally, it has problems on larger scales. That was attitude number two. Attitude number three, which in my mind is the most reasonable one, okay, is the middle ground, is to say, number one, first of all, dark matter must exist to fit those large-scale properties, to fit the large-scale data, and it behaves like a cold collisionless fluid on large scales, but that in fact this MOND phenomenon is not a conspiracy, but it has to be encoded in the microphysical properties of dark matter itself. Now, in this talk, I'm going to give you one example of this. By no means do I mean to say that this is the only way to do it, but through a superfluid phase of dark matter, I'm going to argue that this is actually possible. Okay. So this is really the middle ground. Okay, so superfluidity is really one of the most remarkable properties of quantum mechanics, most remarkable manifestations of quantum mechanics, in my opinion. So you take liquid helium, you cool it down below critical point, its behavior completely changes. From this chaotic boiling phase, it becomes basically this coherent. Basically, the helium atoms stop behaving independently. They behave coherently at that point. Okay? So it's really, truly remarkable. And this is really just becomes a quantum mechanical system at this point. So why in the world would dark matter behave this way? Why is it natural? It's not so crazy to think that dark matter may be a superfluid. There are two necessary conditions for Bose-Einstein condensation. The first condition is that the dark matter should be light enough that in galaxies, it's de Broglie wavelength overlaps. The de Broglie wavelength of different particles overlap. So the de Broglie wavelength, one can plug in the velocity of dark matter particles in a halo, has to be larger than the interparticle separation of the dark matter, and we know all these things. So you can translate this to a bound on the dark matter particle mass, which is of order eV. So these are not WIMPs, but they have to be axion-like particles in order to form a superfluid. So here I've plotted, you see, for a given halo mass, there will be a given virial velocity for the dark matter particle. And as a result, you can plot that at a given, let's say you fix the dark matter particle mass, then for low mass halos will have small velocity, small virial velocity, therefore long de Broglie wavelength, and therefore superfluid. But as you crank up the mass of the halo, the dark matter particles become hotter and hotter, their virial velocity gets larger and larger, and at some point they don't form superfluid. So this will be important in a minute. It says that only light enough halos will form superfluid phase for the dark matter. When you move to large halos, massive enough halos, at some point, this is no longer true. Okay? They behave instead like normal dark matter particles. That's not enough. The second condition is that, necessary condition is that the dark matter particles thermalize. They thermalize with themselves. Okay? So this requires their interaction rate, okay, including the Bose enhancement factor, should be larger than the dynamical time for particles inside the halo. So you can work that out. This translates into a lower bound, rather, on the self-interaction cross-section of the dark matter, which intriguingly ends up being of the order of centimeters squared per grams, which is of order the ballpark figure that people talk about when they think about self-interacting dark matter. Now, there's a well-known observational bound from bullet-like galaxy mergers, which constrains this velocity-independent. Assuming it's velocity independent, it puts a universal bound of 0.5 centimeters squared per gram. So we need the mass to be, because it's to the fourth power, the mass can be a little bit sub-eV, and it happily satisfies the observational bound. Now, you know everything at that point. You know, you can work out, in principle, the critical temperature for this Bose-Einstein condensate of dark matter. You plug in numbers, and you find quite interestingly that the critical temperature for our dark matter ends up being millikelvin. Just numerically ends up being millikelvin, which is interesting because known cold atom systems in the laboratory have critical temperatures of order comparable millikelvin. Like lithium atoms, for example, have this kind of critical temperature, which is suggestive, and this is the point I'm going to I think maybe it's more than just an analogy, that perhaps the dark matter in this theory will behave like cold atoms. Okay, we'll see that there's other piece of evidence for that. Now, as we saw, once you form superfluid, you should no longer think of the dark matter particles as individual particles moving around. They now form a coherent quantum mechanical state. And the relevant excitations are collective excitations, in particular, phonons at low enough energy. And we're told by Landau that if you take a superfluid at finite temperature, subcritical but finite temperature, you should start thinking now, instead of just pure superfluid, it's a mixture of two fluids. It's still one system, but it behaves classically as a mixture of two fluids, two classical fluids. The condensate and then the excitations on top of the condensate. The fraction of particles in the condensate relative to the normal phase is given by this known formula, which is the ratio of T over Tc to some power. The power 3/2 here is for a free boson gas, but you can generalize to include interactions, and that's what we're doing now in the actual dark matter halo, in the realistic case of the dark matter halo. And you find the following. So you find, indeed, that again, let's think about it as a function of the mass, because the mass of the halo gets related to the temperature of the dark matter inside a given halo. So as a function of the mass, therefore, you can compute this fraction of the particles in the condensate. And it's 1, of course, at the low mass end, meaning that you're completely condensed. And as you go to the high mass halos, at the high mass end, dark matter is very hot, and then you end up being at the critical temperature. And then the condensate fraction shoots down to 0. So you see that, for example, if you take 0.6 eV as the particle mass, which will be sort of our fiducial value, you see that galaxies, which sit at this end, are mostly condensed, meaning they're superfluid, whereas clusters of galaxies, which are the 10 to the 14, 10 to the 15 solar mass end, are normal phase. And this will be important when we try to explain why galaxy clusters have dark matter behaving like ordinary dark matter as opposed to MOND. Okay? Yeah? Yeah, so exactly. So exactly whether it's 0.6 or 0.1 or 1, yeah, it's chosen so that. But you see there's a pretty big range, because galaxies sit roughly 10 to the 12 below. Clusters are 10 to the 14, massive clusters 10 to the 14 and higher. So there's some range. I haven't computed exactly, but roughly. I mean, at some point, remember, the upper bound is 2 eV. Cannot be more than 2 eV, otherwise you don't condense even in galaxies. So, okay, so indeed, we're towards the upper end of the allowed region. Okay. Now, as we said, once you form superfluid, so now let's imagine we are in the superfluid state in a galaxy, we should no longer think of these particles as individual dark matter particles, but they actually behave collectively. And we should describe the effective theory of those collective excitations, and at low enough energies, those are phonons. So let me describe for you what is the effective theory of a superfluid. Effective theory of a superfluid is very simple. It's defined, basically definition as a field theory, is that it describes the phase of a global U1 symmetry breaking, spontaneous breaking of a global U1. Okay? And so we know from textbooks that therefore there's a Goldstone boson associated with that global symmetry breaking, and that Goldstone boson is therefore shift symmetric invariant. Okay? There's a mode theta which has a shift symmetry under this U1. But the second condition, in order for it to be superfluid, the state that we're working in is a state that has finite charge density under that U1. Meaning, the charge density, in general, will be proportional to theta dot. That's just from Noether's theorem, proportional to theta dot. And so we're working in a state where the expectation value of J0, the charge density, is non-zero. And if you imagine you can field redefine theta, without loss of generality, you can always pick this VEV for theta in the ground state to be linear in time, just by redefining what theta is. And so this profile, so meaning we're in the state where theta is whizzing around the bottom of the trough. That is a superfluid state. Where mu is identified thermodynamically as the chemical potential. It tells you how many particles are there in the halo at the end of the day. And then excitations on top of this linear time profile, on top of it, these excitations are the phonons, the superfluid phonons. So now, if you write down the most general effective theory consistent with those symmetries, Well, so they have to be invariant under the shift symmetry. So the most general thing at lowest order in derivative, the most general thing you can write down is therefore a P of X. It's a P of X theory. Where X here, I'm assuming a non-relativistic fluid, and so I'm writing down the Galilean invariant kinetic term. And here, of course, I've taken into account the fact that we're working at finite chemical potential. Okay, so this is the most general theory for the phonons, P of X. Okay, so here it is. That's at 0 temperature, by the way, but one can consistently include finite temperature corrections. Let's just stick to 0 temperature for simplicity. So the conjecture, and it's a conjecture, is that this theory of phonons actually is the MOND theory, because after all, this x to the 3/2 that we saw earlier is exactly of the form of the superfluid action. Okay, so in general, we're going to write it in this way. We're going to have the scale. I've pulled out an m to the 3/2 for convenience. There will be a scale out front, which will be the scale of the superfluid. We'll call it lambda. And here is the x to the 3/2. And don't be distracted by the square root. This is not so important for our purposes. At the end of the day, it's x to the 3/2. Now, you're going to say, this is equally ugly as what we said at the beginning, because it's still a non-analytic power. But we'll see that the moment you think of it as a superfluid, this non-analytic power takes a different meaning, and it's actually much more palatable. Okay? But let's stick to this for a second. Now, eventually to get the MOND law, what we want, so the phonons will eventually mediate the MOND force between baryons. And so we need to couple the phonons in some way to the baryons, and the simplest way to do it is to couple them, again, through this conformal coupling. It explicitly breaks the shift symmetry of the phonons, but it's going to be suppressed by M Planck. So it's a technically natural breaking of the shift symmetry. And it's the same scale lambda that appears here and here. And this scale lambda, to match to the MOND acceleration scale, this is just the usual numerology. You turn the crank, and you find that it's this geometric mean between A0 and M Planck, which ends up being milli-electron volt. Which is interesting, because at the end of the day, in this theory, there are two scales, really. There's the mass of the dark matter particle, which we said was over EV. And now lambda, which is the strength of the coupling, as well as the normalization of the P of X, also ends up being roughly electron volt, milli-electron volt, but close enough. Okay, so from particle physics standpoint, all the scales are of order MeV. So now, why is it more palatable to have x to the 3/2 when you think of it as a superfluid? So there are known examples in nature that exhibit this non-analytic feature. Okay, so that to me was what really got me thinking about dark matter superfluidity. There's a system known as the unitary Fermi gas, where you basically take a gas of fermionic atoms, you tune them to infinite scattering length. Okay, you tune them to unitary limit, S-wave unitarity. And at that point, it's really the transition between describing the fermionic gas at low temperature as a Bose-Einstein condensate or as a BCS. It's really the middle ground of the two. And this transition is this unitary Fermi gas. And since the scattering length is going to infinity, there's no scale in the problem. And so this effective action for the phonon is purely determined by scale symmetry, and it's x to the 5/2. Okay, so this is a known studied example in nature. We need x to the 3/2. It's also indicative, at least suggestive, that the type of interactions between our dark matter particles is a three-body interaction. Okay, and here's why. So you know the textbook way to get a superfluid effective description is to use a complex scalar field. That's our U1 field in the weakly coupled regime. That's how you do it. But normally in textbooks, you would take a quartic coupling for the complex scalar field, psi to the 4th, which would describe 2 to 2 scattering. If you instead take psi to the 6th, which is 3 to 3 scattering, okay, and you do the usual thing, you split your wave function as a radial mode, which is massive, and your goldstone, you integrate out the massive mode. In this case, if it had been psi to the 4th, you would have found x squared at the end of the day. That's the textbook result. But if you take psi to the 6th, you find x to the 3/2. So again, not crazy. It just indicates some three-body interaction. Unfortunately, the sign, if you just take this naive theory, the sign doesn't work at the end of the day for the x to the 3/2. So you get the wrong sign at the end. Okay, so it cannot be that simple, but it's, again, indicative of a three-body process. Okay, so now that's the theoretical story. Now the phenomenology of it. Once you know the P of X, you know everything that you need to know about the condensate, about the superfluid. In particular, P of X tells you the grand canonical equation of state relating pressure to the chemical potential, and you can turn the crank through the thermodynamic identity to actually find the pressure in terms of the energy density. And in this case, for x to the 3/2, for this particular relation, it gives you P going as rho cubed. Again, it's interesting, right? It's not a crazy equation of state. P going as rho cubed. Polytropic, it's a polytrope. Okay? And for the experts, of course, people have studied Bose-Einstein dark matter for a long time, and in their case, it was always rho squared. So here it's a different equation of state, it's rho cubed. So with that, assuming hydrostatic equilibrium, you can work out the density profile of the superfluid bubble, if you want, inside the galaxy. You can work it out, and it looks like a chord. It's a chord density profile. It obeys the Lane-Emden equation, so it has this kind of profile. This is the pure superfluid bit at 0 temperature. And this is remarkable once you plug in numbers. So it's a conspiracy. The Planck scale is, of course, 10 to the 28 eV. And a solar mass in electron volt is 10 to the 66. Okay, so you put this all into the sausage factory, and out comes big numbers combined, and they give you kiloparsec. Okay, so somehow with a 10 to the 12 solar mass bubble, which may be a little too much, but okay, so some bubble of order galactic mass, and our parameters of order natural values, you get 20 kiloparsec. Okay, and this is just a conspiracy, like I said, of 10 to the 66 eV, 10 to the 28 eV, put it all together, you get kiloparsec. Okay? So interestingly, you get cores that are realistic size for our parameters. Now, in truth, it's not at 0 temperature. Okay, halos are at finite temperature. So here's how the profile would look like. Though in the moment, we are currently trying to derive this from condensed matter description. But at the end of the day, here's how it's going to look like. You have the superfluid bubble, which was mostly constant density. Okay, so if you look at this profile I just showed you, it's mostly constant. It goes to 0, but it's pretty constant. It doesn't change by orders of magnitude until it hits the critical radius. So it's approximately constant. And then it's matched on to an isothermal bubble, which is just the dark matter particles in a normal phase, but with an isothermal profile. And finally, you expect eventually you revert to a 1 over R cubed profile. So this, for the aficionados, this is like a Burckhardt profile. It approximates a Burckhardt profile. So these are preliminary results with my colleague Benoit Famé. We started fitting rotation curves. This does not include all the physics, so I'll be honest with you. This does not include all the physics, but it's just to give you a taste of how this is going to come out. So remember, we have the dark matter, which is gravitationally doing its thing, but also there's the phonon-mediated force, which is giving rise to MOND. So I'm going to explain to you how this curve looks like, the different components. Okay, so for the rotation curve here, you have the the dotted red curve are the baryons, the contribution to the velocity curve from the baryons. And the dashed blue curve is the contribution of the dark matter itself, just the gravitational effect of the dark matter. And as you can see, and the dotted points, of course, are the data. So you see that the dark matter itself doesn't do very much in this case to explain the rotation curve. Instead, the rotation curve, the difference of the two is the phonon force. So you see here all the action is coming from the phonons. And of course, because MOND was doing pretty well, by the way, this is the same galaxy I highlighted at the beginning, okay, 2574. And because MOND was doing pretty well at fitting it, now, of course, in this case as well, it's doing pretty well. The contribution for the dark matter itself is quite small. And for reference, for these parameters we chose, in this case, the core is about 30 kiloparsec. This is a low surface brightness galaxy. If you take a high surface brightness galaxy, here's another poster child. Here's a poster child high surface brightness galaxy. Again, now here you see the core is, in this case, 76 kiloparsec, and the rotation curve is probed all the way to 60. So now think about it. The dark matter distribution is approximately constant within this core, okay, meaning that the mass of the dark matter grows as R cubed, as the distance cubed from the center. So as you approach, it's pretty small near the center, but as you approach the edge, it becomes increasingly important. And that's what you see here with the dashed blue curve. You see at the end, the dashed blue curve rises up and becomes more important as a contribution. And you'll notice that whereas MOND would predict an exactly flat rotation curve at the end, you see in the data a slight tendency to rise up. And this we see the rising up also in our case due to this. It's not a very statistically significant effect, but it's nice to see the trend is explained with our dark matter contribution. Okay, I don't know, how am I doing in time? 10 minutes, perfect. Okay, so I'm going to go quickly over this. At some point, of course, you have to worry, when does the effective field theory break down? Okay, it's an effective theory, so where does it break down? In particular, the velocity of the superfluid is given by the gradient of the phase. So if you have two large gradients of the superfluid, it's telling you that the local velocity of the superfluid gets large, and eventually it could exceed the Bose-Einstein condensate critical velocity, which you don't want. This would be the breakdown of the effective theory. But you can show that in galaxies, these gradients are pretty small, except in the very central regions of order kiloparsec. Okay, so effective theory is valid everywhere except within the inner kiloparsec of the galaxy. However, if you ask in the solar system, the MOND acceleration, although a small correction to Newtonian gravity, is too large to be acceptable based on planetary data. Okay, if you just add this extra square root contribution to the force. So you have to wonder, does that mean we're ruled out, theory is ruled out just based on solar system tests? Of course, you could complicate the theory further, okay? But here, actually, there's a very nice resolution. It turns out the sun itself creates such a huge gradient in the superfluid profile that it actually violates this effective theory bound. So in fact, what happens is that within the solar system, effective theory is no longer valid, and what you have are really just dark matter particles whizzing around. That's the UV completion, just dark matter particles whizzing around. So there's no coherent force between planets and the sun as a result. And that's very nice also in principle, although you don't have to. But these are axion-like particles. You can couple them to standard model the way you couple axions. And they can in principle be constrained by axion detection experiments. Of course, here the mass is of order EV, so it's futuristic for axion detection. But still, it's interesting that in principle it can be done. All right, I'm going to move on to observational signatures. This is the dessert, okay, for this story. So what are some of the signatures? If dark matter really is a superfluid in inner regions of galaxies, what do you expect? So first of all, as you know, you cannot rotate uniformly a bucket of helium, liquid helium, above a certain critical angular velocity. It doesn't rotate uniformly. It forms an array of vortices. So, and you can compute easily, based on dark matter simulations, what is the typical angular momentum of a halo, of the dark matter halo. And you can compute that it's well above the critical velocity for forming vortices. So we expect there's tons of vortices inside the galaxy. In fact, you can estimate that there's about 100 of them within the size of the solar system. Okay? So that's kind of interesting. And just to show, people experimentally in liquid helium have done a lot of nice experiments. And these vortices, they're not just standing still doing nothing. They interact, they recombine. Okay? So I don't know whether this will be. Unfortunately, these vortices that we're talking about, they're millimeter in radius, okay? So they're very thin. They're not very massive. So gravitational lensing effect probably are not very significant. But still, it's interesting to study what they will do. OK, now, for structure formation, there's a very interesting story about mergers. So as you know, in the standard story, mergers proceed in CDM through dynamical friction. Okay, halos come in, but because of dynamical friction, halos are quite efficient at merging themselves. Now here, on the other hand, if it's superfluid, one has to revisit the story a little bit. So we know from Landau that if you have two superfluids that collide with each other, if their infall velocity is less than the sound speed, they will pass through each other unimpeded. Okay? If they come together in with a supersonic relative velocity, instead they will excite the condensate will excite itself out of the condensate, create excitations, and then you have standard normal phase story. So for galaxies, we expect that if the infall velocity of galaxies is subsonic, then you expect galaxy superfluids to pass through each other with negligible dynamical friction between the dark matter. Of course, the stars still have dynamical friction among them, but it's reduced compared to dark matter. Whereas if the infall velocity is supersonic, then you expect to excite dark matter particles out of the condensate and have significant merger rate, just like in CDM. Now, this is interesting for some systems. In particular, there's some nice little puzzles in the data. One of them that's been known since the 70s is the Fornax classical dwarf. Okay, so Fornax is one of the classical dwarfs around the Milky Way, and it has five star clusters in orbit around it, about roughly 1 kiloparsec about the center of Fornax. Now, if you had a normal dark matter dark matter profile for Fornax, due to dynamical friction, you would have expected these star clusters to find their way down to the center and form a star cluster at the center of Fornax, which they haven't. Okay, so that's an interesting puzzle. I mean, within dark matter, people can explain this perhaps if there's some very cored dark matter distribution in Fornax, and these guys are just sitting outside the core. But for us, it's explained simply by the fact that these guys are just happily swimming in a superfluid bubble of dark matter around fornax, and therefore are not slowed down by dynamical friction. There's another interesting observational tension, if you want, which comes from the two-point function of LRGs. So we're familiar with the two-point function of LRGs at very large distances. 150 megaparsec gives rise to the famous BAO feature. But people, of course, have probed this two-point correlation function down to very small distances. This is a deprojected correlation function in real space, OK? So you see that to a very good approximation, this two-point correlation function basically behaves like 1 over r squared, down to exquisitely small distances. We're talking here about tens of kiloparsecs at those distances. At those distances, the individual halos of LRGs are basically overlapping. No? So at some point, you would expect that there should be some feature at tens of kiloparsecs. This is the one halo term shown here. Some feature due to dynamical friction or other effects that would cause these LRGs to merge. And instead, the 1 over r squared persists. Okay? So this is Andrew Kraftsoff that showed this to me. There are even pictures on the web. This is a particular cluster. You see, near the center, you see 3 LRGs near the center. You see it by eye. Okay? So why these guys? In fact, these authors, they put an upper bound on the merger rate of LRGs, basically based on this observation. Okay? So again, in a cluster, I told you, you're mostly normal phase, but near the center, of course, you will have a superfluid bubble. And so these LRGs would be swimming in the superfluid dark matter phase. Okay, so these are more minor, but still things that people talk about. Why we see galaxies that don't have much of a bulge. Again, bulges are disrupted or created if you have lots of mergers. If you can reduce the merger rate, that's probably a good thing. Also, galactic bars. Why galactic bars don't slow down and grow. Okay, if they're swimming in a superfluid, that's very nice. You can keep them small and rapidly rotating. So here are experimentally, people have looked at, indeed, cigars, if you want. So this is mostly one-dimensional. Cigars of Bose-Einstein condensates colliding. Okay? And you see what's interesting. Ultimately, when they emerge, as advocated, they've basically reassumed the shape that they had initially, okay, telling you about this process. But you saw in between, when they're overlapping, you saw fringes. You saw dark, bright solitons. This is due to the quantum mechanical nature of the wave function inside the solitons. Okay? So this is a purely quantum mechanical effect. And some group did some simulations. This is not of this particular superfluid I'm talking about, but of fuzzy dark matter, in which you see that you're going to see a halo merger, but you basically see the emergence of fringes as well in those simulations. Okay? So you expect, so how would you see those? I don't know. Maybe through lensing eventually. One could speculate that this could be an added contribution to the process that gives rise to shells around galaxies. Of course, we know a very common way to do this, but this would be an added mechanism that could do it. Okay, so now I want to tell you also, I want to stress this is not MOND. Okay, so for anybody whose blood pressure has risen, it's not MOND, okay, to be clear. It has MOND as an emergent effect of dark matter, and it has distinguishing feature from MOND, and that's important for me. So, because it's not all roses for MOND. So I want to make 2 points about this. Globular clusters, to a large extent, are fitted without dark matter. There's no evidence for dark matter in globular clusters. They're just baryons with Newtonian gravity. It's a problem for MOND in the following sense. The nearby globular clusters, okay, so of course their internal acceleration is well in the MOND regime. So you would expect that from a dynamical point of view, you'd expect that there's missing mass in the, okay. But in MOND, it's actually subtle, because if you're close to a bigger object like the Milky Way, there's what's called the external field effect, which tends to screen the MOND effect in the system which has even a small, tiny internal acceleration. So you have to look for objects, globular clusters that are far away. And that's what people have done in some cases, like this object by Rodrigo Ibata, okay, in which you find that indeed this distant globular cluster doesn't need to have any dark matter in it, and so it's potentially problematic in MOND. For us, it's very interesting, because these distant guys, they're outside the superfluid bubble. And if you're outside the superfluid bubble, then there is no MOND, okay? Furthermore, for them, these globular clusters themselves don't have, if for whatever reason they don't have dark matter, just like in CDM, then again, you don't expect MOND. So that's not in tension with us. Tidal dwarf galaxies, these are galaxies that are formed in tidal process of near mergers of galaxies. They're recycled galaxies. They're formed from the stuff that emerged from the tidal stripping. You don't expect those objects to have much dark matter. And in fact, when you do an analysis of 7 of such objects, you find there's no evidence for missing mass in those guys. That would also be problematic for MOND. In principle, it's not problematic for us because if you don't strip off much dark matter, which is what you expect, then these guys should be dark matter free and therefore MOND free. And this is for the MOND aficionados, if there are anybody in this audience. And if there's anybody, they probably wouldn't even raise their hands. But okay, if in your heart you're a MOND aficionado, this is also to show some class of object which is very interesting. Actually, purely observationally, it's actually super interesting, these objects. These are known as the ultra-diffuse galaxies. So people have discovered, in Coma cluster, they've discovered up to 1,000 of galaxies which are very diffuse objects. They're the size of the Milky Way, okay, in terms of size, but their luminosity is about 1% of that in Milky Way, so extremely diffuse objects. And those objects, because they're so diffuse, you'd expect they would be susceptible to tidal stripping as they're moving in the deep potential well of the cluster. You'd expect they would have been tidally stripped. The fact that they've survived means, in the standard picture, they must be surrounded by a pretty massive dark matter halo. So they have mass-to-light ratio of order 200, okay? Now, in MOND, that's perfect. You would say, great. These guys, have small accelerations, perfect. Therefore, in MOND, you would expect to have also big dynamical mass-to-light ratio. But the problem is, again, this external field effect. Okay, it's a subtle argument, but the external field effect would tell you, well, they're in a deep acceleration well, and therefore, they should not exhibit a mass discrepancy in MOND. So the fact that they do is problematic for MOND. But in our case, it's not, because as you remember, inside this cluster, you are in a normal phase, so there's no external field effect. But they do have their own superfluid bubble around them, and therefore you expect a local MOND phenomenon for these objects. Okay, so it's very nice. Okay, very nice. So it seems to work that there is no external field effect in this, just as we predict. Okay, I'm going to leave you with some thoughts. So here I presented to you this sort of one example of a middle ground between having dark matter and yet reproducing properties that we observe with galaxies. I've done it with superfluidity, so it's just a way to show that somehow MOND and dark matter are just 2 phases of the same underlying stuff. From a particle physics standpoint, the effective theory of the phonons I've shown you is reasonable, I think. You know, all the mass scales of order electron volts. And from an empirical, from phenomenological point of view, if there's no dark matter, then there's no MOND. So it has distinguishing feature from ordinary MOND, which is good. It doesn't kill dinosaurs, okay, if you wondered. So it's dinosaur friendly. And then there's some open questions that you can ask, okay? So I think the most interesting one is there a cold atom or condensed matter system in which this equation of state arises? As we've shown, this will be very nice. Now, if you have a cold atom superfluid that has this equation of state, in principle, you could go in the laboratory and simulate. That's the dream. No, simulate galaxy interactions with cold atoms. That would be the dream. Like we said, this is not crazy. It's suggestive of 3-body interactions. In particular, if you just think naively in the virial expansion of the equation of state, ideal gas being the leading term, rho squared being 2-body, rho cube is suggestive, again, of 3-body. And there are many ways, this was just one way that I showed it, that you can get superfluidity, MOND arising with superfluidity. After all I'm using is that superfluidity gives you a classical scalar field, okay, the phase of the wave function. And of course, the elephant in the room is, how does dark energy fit into this? It would be so compelling if somehow dark energy were yet another phase of the same substance, somehow. Thank you very much.
All right. We have time for maybe 2 questions. John?
There is data available for the Milky Way galaxy with its traces. And the data goes out to from 40 kiloparsec to 200 kiloparsec. And MOND's rotational velocities or dispersion velocities are flat, and it doesn't fit, significantly not. But this modified gravity theory has a parameter-free prediction that fits. So the question is, what happens with your...
Yeah, this is very interesting.
MOND?
So, right, so you're saying it's not just rotation curves, of course, that we can infer something about dark matter profile. We can, in principle, looking at the velocity dispersion of satellites and so forth. So this is the cartoon profile that we have. You have superfluid, which, say, for Milky Way, will be of order 50 kiloparsec. Think about it that way. That's the radius of superfluid, within which you have the MOND phenomenon. And now you go outside, and you have what I think is isothermal, and further out, something that goes to 1 over r cubed. Now, by the way, as you go from the superfluid core to this guy, here you have the MOND force, and here you don't. So this will look like a negative mass shell from a Newtonian standpoint around the superfluid, because if you're here, right, you know. But this is interesting because it's also a prediction that somehow rotation curves should not extend past the superfluid radius, because this would be, if you're a baryonic particle, a gas particle here, there's an instability. If you're kicked out here, you feel negative mass, and then you ooze out. Yeah. So I think a priori there is no contradiction with velocity dispersion of satellites or anything like that. It's not MOND all the way. It reverts to just this is like a Burckhardt profile, effectively. So.
Any other?
So the temperature you quoted for the superfluid, it was millikelvin.
Yeah.
So that's quite a bit colder than the CMB.
Oh yeah.
Do you have to worry that like it was in equilibrium early on?
Oh yeah,
so
it's never in equilibrium. So it's like yeah. So given that the coupling is M-Planck suppressed, you never thermalized with ordinary matter, which is good because these are axion-like particles. You never want. So yeah, that's a good point. They're thermal with themselves. They're like axions, except that they thermalize with themselves at a very low temperature. They don't thermalize with the rest of the matter.
All right. Maybe in the interest of time, Jean-Luc, do you want to go get set up? Well, let's thank Justin one more time. Actually, maybe.